Hi everyone, welcome to Unit 25 of online course on probability distribution. In the last session, we have defined negative binomial distribution, its different versions of probability mass function, and now we are finding mean and variance of the negative binomial distribution. So, in this module, we included the method of finding mean, variance, probability generative function, moment generative function of negative binomial distribution. And we have defined the negative binomial distribution as the probability mass function of the negative binomial distribution with parameters R and P. Suppose X is a negative binomial random variable with a parameter R. R is the number of success, R successes, and P is the probability of getting success. And we have the probability mass function for value f of x that can be described in this form: x plus r minus 1 c x p power r q power x, where x is equal to 0, 1, 2, 3, etc., and p plus q is equal to 1. So, how do you find the mean and variance of this random variable or negative binomial distribution? Now, what is the mean of the distribution? So, mean is given by expectation of x, and that is equal to sigma over x, x into f of x. For a discrete random variable, we know the mean is equal to expectation of x is equal to sum over x values x into f of x. So, you find this value by substituting f of x here, that is, here x is equal to 0 to infinity x into x plus r minus 1 c x p power r q power x. And how do you find the value of the mean, and how do you simplify this expression? And this is equal to sigma over x is equal to 0 to infinity. We know this is x plus r minus 1 factorial divided by, if you are considering this expression, x plus r minus 1 c x, this is x plus r minus 1 factorial divided by x factorial and r minus 1 factorial, and x is here, and p power r q power x. Or that can be written as sigma x is equal to 0 to infinity, this x and x factorial common factor cancelled. So, this is x plus r minus 1 factorial divided by x minus 1 factorial, r minus 1 factorial, p power r q power x. So, this is the final expression of expectation of x after substituting f of x value. Now, to get the sum of this expression, we are make use of the concept of the negative binomial probability mass function. You know, sum of f of x is equal to 1, and that is sigma x plus r minus 1 c x p power r q power x. This is 1, we know. See, that is sum of the probability mass function over all x values is equal to 1, So, that is sum over x, x plus r minus 1, c x p power r q power x is equal to 1. So, using this concept, we can find the expectation of x. Earlier we have expectation of x, in the last expression we have expectation of x is equal to sigma over x, x plus r minus 1 factorial divided by x minus 1 factorial, r minus 1 factorial, p power r, q power x. That was the last expression we have. Let me write this expression as sigma over x. Instead of this x, let me write it as x minus 1, then r plus 1 minus 1. See, this is x plus r minus 1, let me write like this, divided by x minus 1 factorial, r minus 1 factorial, p power r, q power x. And this is equal to sigma over x, x minus 1 plus r plus 1 minus 1 factorial, or let me x minus 1 plus r divide c x minus 1. Okay. So, this is x minus 1 plus r c x minus 1. And to get that, we need one n r here. Okay. And let me make this p power r, and here it is r, instead of r we have r plus. So, let me write this p power r plus 1 and q power x minus 1 q divided by p. So, altogether these are the changes, that is sigma over x. This expression is written as x minus 1 plus r plus 1 minus 1 factorial divided by x minus 1 factorial r minus 1 factorial p power r q power x. You make this factorial. You make, to make r minus 1 factorial as r factorial, you multiply by r and make p power r, and so as p power r plus 1 divided by p. And q power x minus 1, q power x as q power x minus 1 into q. The advantage is this is equal to, see, r into q divided by p is taken outside, this r, q and this p. Okay. Then remaining sigma over x, x minus 1 plus r c x minus 1 p power r plus 1 q power x minus 1. And this is nothing but, using this expression, this is nothing but 1. So, this is equal to r q divided by p. We have r q into p is the expression. Hence, for a negative binomial random variable with the parameters r and p, mean is equal to r q divided by p. After deriving the mean of the negative binomial distribution, our aim is to derive the expression for variance. And to get the variance, first we find the factorial moments, expectation of x into x minus 1. And based on that value, we can calculate the variance of x. How do you find the expectation of x into x minus 1? And to get the expectation of x into x minus 1, as usual, we have the formula summation over x, x into x minus 1, x plus r minus 1 c x p power r q power x. And this is the negative binomial probability mass function. And this is x plus r minus 1 factorial, x minus 2 factorial, r minus 1 factorial, p power r, q power x. And this is obtained by this x into x minus 1 and this x factorial. There will be an x factorial, common factors are cancelled. And this is equal to, we can make this r into r plus 1 into, see, this is actually r minus 1 factorial, and r minus 1 factorial, in order to make this r minus 1 factorial to r plus 1 factorial, you have to multiply r into r plus 1 and you make q square, you take these factors here and then the remaining factors you have considering. So, this instead of this p power r, we have consider this p square. So, this become p power r plus 2 we have to write, and we have q power x here. So, this is q power x minus 2, okay, and this other factors are x minus 2 plus r minus 2 minus 1 c divided by c of x minus 2, this expression. So, this is nothing but our f of x value. So, after cancelling the common factors from x factorial x into x minus 1, our aim is to write this expression as an expression of the f of x value. The f of x is negative binomial distribution around a probability mass function. And to get that value, you take r into r plus 1 q square divided by p square outside the parts of the sigma sign, summation sign, then remaining factors will reduce to an f of x, the probability mass function of the negative binomial random variable. This procedure can be adopted to find all factorial moments of the negative binomial distribution. So, finally, we have this x r into r plus 1 q square divided by p square. This is our expectation of, so expectation of x into x minus 1 is equal to r into r plus 1 into q square divided by p square value. And after getting the expectation of x into x minus 1, how do you find the variance? And we know the variance is equal to expectation of x into x minus 1 plus expectation of x minus the expectation of x the whole square. And already we have the value of expectation of x into x minus 1 as r into r plus 1 q square divided by p square, and expectation of x already calculated as r q divided by p, and expectation of x the whole square as r q divided by p the whole square. And simplifying this expression, you can see this is equal to r square q square plus r q square plus r p q minus r square q square divided by p square. Okay. So, taking p square common, so this become r square q square r q square plus r q into p and minus r square q square. So, this will be cancelled, and this is equal to r p, r q is common, q plus p divided by p square, and r q plus p is equal to 1. So, this is r q divided by p square. So, expectation of x into x minus 1 and expectation of x value that are substituted in the variance formula, and then after simplifying the expression, we have the variance r q divided by p square. Just not for a negative binomial random variable with the parameters r and p, mean is we obtained as r cube divided by p, and variance is equal to r cube divided by p square. On the basis of these two values, mean and variance, what is our conclusion? The conclusion is, see, for the negative binomial distribution, we have obtained the variance as r cube divided by p square and mean as r cube divided by p. Which is larger here? See, p is a value in between 0 and 1. So, variance of x is r cube divided by p square is of course larger than mean value r cube divided by p. So, this is an important property for the negative binomial distribution. Since variance is obtained as r cube divided by p square and mean is equal to r cube divided by p, and since p is a value in between p and 0 and 1, this value mean is less than variance. Mean is less than variance for the negative binomial distribution. So, in the case of binomial random variable, the mean and variance, NP and mean and variance, mean is equal to NP and variance is equal to NPQ. And in the case of the Poisson random variable, mean is equal to lambda and variance is equal to lambda, that are equal. So, negative binomial distribution is an alternative to the Poisson distribution. That is, suppose we want to model certain physical situations that can be modeled by Poisson distribution also, similar character. But in that case, suppose the observed variance is greater than the observed mean, we can use the negative binomial distribution as an alternative to model that physical situation. And now our aim is to find other quantities related with the negative binomial distribution, other quantities, especially some functions, that is probability generative function, moment generative function, cumulative generative function, etc. And very easy to establish the values here because the negative binomial probability mass function, using the concept of the negative binomial probability mass function and using some properties of that, we can establish the probability generative function value and moment generative function value very easily. And what is the probability generative function? See, for a negative binomial random variable with the parameters r and p, the probability generative function value is given by this expression p power r 1 minus q s power r, or we can write p divided by 1 minus q s all power r. This way also we can write. And the derivation of this probability generative function is very easy. See, by definition, the probability generative function value is equal to expectation of s power x, and that is equal to summation over x, this is summation over x power x plus r minus 1 c x p power r q power x. And what we are doing here is this is equal to sigma over x plus r minus 1 c x p power r, and this q power x and s power x are combined, and we can write this q s power x. And this is equal to p power r sum over x plus r minus 1 c x q s all power x. And this is a standard value, we know this is 1 minus q s all power minus r, because already we have the x plus r minus 1 c x q power x is same as 1 minus q power minus r. This is a known result for us. Sigma over x x plus r minus 1 c x q power x is equal to 1 minus q all power minus r. So, based on that, the summation over x, x plus r minus 1 c x q s power x is 1 minus q s. Instead of this q, we have q s power minus r. So, p power r 1 minus q s power r is the value p s, sorry, this is, sorry, p power r, this is p power r divided by 1 minus q s power r, provided this s 1 minus q s is less than modulus q s is less than 1 or q s is less than 1. So, or s is less than 1 by 1 minus p. So, we established that probability generating function of the negative binomial random variable as p power r divided by 1 minus q s power r or 1 minus p s power r, because q is equal to 1 minus p, provided s less than 1 minus p. Similarly, we can establish the moment generative function also. The similar procedure we adopt in order to derive the moment generative function also. How do you find the moment generative function? So, for the negative binomial random variable, the moment generative function is given by p divided by 1 minus q e power t or power r, when q e power t is less than 1 for a negative binomial random variable with the parameters r and p. And we know the definition of the moment generative function. Moment generative function mxt is equal to expectation of e power tx, and that is summation over x e power tx cube x plus r minus 1 c x p power r q power x by substituting the probability mass function value of the negative binomial random variable. Okay. Then, as in the previous case, here also we are comparing the factors p, that is p power r is taken outside, x plus r minus 1 c x e power t q power x, and that is p power r. See, this is again a known result for us, because sigma over x, x plus r minus 1 c x q power x, that is that value is 1 minus q all power minus r. This is this result we apply here. This is here x plus r minus 1 c x e power t q all power x. So, this is 1 minus q, instead of q we have q e power t all power minus r. So, the moment generative function is equal to p divided by 1 minus q e power t all power r, provided this q e power t is less than 1 or e power t is less than 1 by q. So, these are the two important functions, that is probability generative function and moment generative function with respect to the negative binomial random variable with the parameters r and p. See, for the negative binomial random variable, moment generative function is p divided by 1 minus q e power t all power r. After getting the moment generative function, we can verify the additive property of the distribution. That is, we have, suppose we have n independent negative binomial random variables. Let x1, x2, etc. up to xn be n independent negative binomial random variables, and each xi has a negative, each xi has parameters ri and p. See, so suppose xi follows negative binomial random variable with parameters ri and p, where I is equal to 1, 2, etc. up to n. See, the probability of getting success is common to all the random variables. negative binomial random variable. So, x1 is a negative binomial random variable with R1p parameter, x2 is a negative binomial random variable with R2p as parameters, etc. So, if it is, what is the problem is to find the distribution of sum of the random variables x1 plus x2 plus etc. up to xn, and the result is the sum of the random variables also a negative binomial random variable, and with parameters sum of the parameters r1 plus r2 plus etc. up to rn, and second parameter of course the probability of getting success p. So, this is known as the additive property of the negative binomial distribution. And to prove this additive property of a distribution, we usually make use of the moment generative function to establish the result. That is, the xi follows negative binomial with RIP, and already we established the moment generative function is equal to p divided by 1 minus c for the negative binomial random variable with the parameter r and p. mxt is equal to p divided by 1 minus q e power t all power r. This is the expression we established related with the moment generative function. So, the moment generative function of first random variable x1 or xi is equal to p divided by 1 minus q e power t r. Instead of r we have ri. And consider the moment generative function of the sum of the random variables. Sum of the random variables, moment generative function of sum of xi's, that is equal to product of the moment generative function of the respective random variables, because you know xi's are given as these are independent random variables. So, if xi's are independent random variables, the moment generative function of sum of the random variables is equal to product of the moment generative functions, and that is m of sum of xi's is equal to mx1t into mx2t etc. up to mxnt. You just substitute mx1t, that is 1 minus p divided by 1 minus q e power t all power r1. This is this value you substitute here, and 1 minus p divided by 1 minus q e power t all power r2 etc. up to p divided by 1 minus q e power t all power rn. Combining the factors, we have p divided by 1 minus q e power t all power r1 plus r2 plus etc. up to rn, or sum of ri's. And from this expression, this is similar to the moment generative function of a negative binomial random variable, and by uniqueness property of the moment generative function, that is, for a random variable we have on the basis of the moment generative function we can identify xi's distribution. So, by uniqueness property of the moment generative function, from this expression we can identify that this sum of xi's follows by negative binomial with the parameter instead of r we have sum of ri's. So, this is the result. So, that means after deriving the moment generative function, we have established the additive property of the negative binomial. So, these are the properties related with the negative binomial distribution, and again we have to discuss negative binomial distribution in another form, and also we can establish that negative binomial distribution as a limit form of the Poisson distribution, and that we will discuss in the next session. So, with this we wind up this session. Thank you for listening. Thank you once again.